So hi there. Often you have something like a battery or a constant voltage source or power source, so 9 volts, 0 volts. And what you want to often have, for example, with Arduino circuits and such, you want to have 5 volts or you want to have other voltages. And what you can do is you can take your 9 volt battery, so that's the symbol here for the 9 volt battery. And you can let this is the positive side, the right side. You can let the current flow through 2 resistors and then back to the negative terminal of your battery. And as the current flows through here, there is a current through the first resistor. And because of that, a current through a resistor always leads to voltage across the resistor. And the current flows through the second resistor, and also there is a voltage drop then across this resistor. And how the current and the voltage are related here, one can find out by the law of Ohm, U equals R times I. So you want to have the voltage across the resistor, you just take the resistance of the resistor. Every resistor has resistance value, and you multiply it by the current that is flowing through it, and if you take these two together you get the voltage across the resistor. So if we imagine it, if we have here this resistor is 1000 ohm, so 1000 ohm, and the second one is also 1000 ohm. So we want to have the voltage across these resistors, and as they are equal, the same current will be flowing to them. The same current, they have the same resistance, so current and resistance is the same through them, and so they have the same voltage across them. And if these two have the same voltage across them, then it can only be that it is 4.5 volt, half of what is here, because then we have 4.5 volt here, 4.5 volt here, and 4.5 volt here. And that's a voltage divider. So we split the voltage in half. We lose from 9 volt 4.5 volt to here. So where are we left with here at this point? Yeah, we are left with 4.5 volt here. And then we lose another 4.5 volt from here to here, and we're left with 0 volts. And a wonder, that is good, because you really are directly connected to the negative terminal, to 0 volts, and that's really what should happen. And what you just produced here is a voltage divider, yes, but you can also see it like this, that here at this point you have created 4.5 volts. From 9 volts you have created 4.5 volts at the output. And you can use this 4.5 volts to, let's say, connect a motor or some other, the electricians say some other load. So let's say, and often a load is symbolized also through a resistor. And let's say we connect here this new resistor here. And then if we really want to have current going through it, we have to connect it back to 0 volts. But now the thing is, let's look at the situation. Let's say this load, it has a resistance of, let's say, 50 ohm. That is quite common. Okay, but is then the situation we had before, where there was the same current flowing through the same resistors here, when we have this 50 ohm here in parallel to this 1000 ohm resistor, is it still the same? Apparently it's not, because whatever current will flow through here, through the first resistor, the current flowing through here will divide up here to here and to here, and some amount of current will be flowing through here and some amount will be flowing through here. When we had only the two 1K resistors, you could calculate the current. Okay, you have 9 volt across these two resistors, when you think of when these are lit here. And so we're solving now for I. This means I equals U divided by R. And before we had 9 volt over the two resistors, and the two resistors in sum, they were in series, and so it was 2000 ohm. And then you have 4.5 milliampere were flowing through each of the two resistors. Now that we have this 50 ohm resistor in parallel, our whole resistance here is not 2000 ohm, not 2 kilo ohm, because now we have to respect this 50 ohm resistor. And as you know, how do we calculate a parallel resistance? So if we say, okay, we have a 1000 ohm parallel to 50 ohm, then that resistance is 1/1000 ohm plus 1/50 ohm to the -1. That's the general rule for parallel circuits. You invert every single resistor, add them up, and then at the end invert the whole sum again. And then what we can do here, we can simplify what is written in there. It is really 50 plus 1000, and in the denominator we have 50 times 1000, so 50,000. So we have here ohms, and we have ohms squared to the -1, and that equals, so we just turn it around, then we are left with 50,000 ohms squared divided by 1050 ohm, and that is 47.6 ohms. And so that whole below construct here of the two resistors, it has only a resistance of 47.6 ohm. And that's the general rule. You also can remember in a parallel circuit, if you look at parallel resistors, then that parallel construct always has a lower resistance than the lowest resistor you can find in the parallel construct. So 50 ohm was our lowest resistor, and if we calculate, no matter if there were additional parallel resistors here, then we are sure we're going to get lower than the lowest resistor. So 47.6 is lower than the lowest, lower than 50 ohm in sum. And so if we now want to have the current going through this construct here, we have to calculate the current when there are 1000 ohms in series with this 47.6 ohm down here. And we calculate that. We say, again, using the formula up here, I, and I make it IP for I parallel, equals, again, the whole 9 volt over the, and now 1000 plus the 47.6 is 1047.6 ohm, 8.6 milliamperes. And you see the current has gone higher. Before we had 4.5 milliampere when there were two 1K resistors in series. Now that we have in parallel this load, which we want to drive, now all of a sudden there is a different current going through here. And if we look then, what we have clearly 9 volt before the first resistor, And let's imagine the situation, okay, when there are, to this 1K resistor, they are going 8.6 milliampere. What voltage is dropped across this resistor? And we calculate this by using a formula. Voltage equals resistance times current. In our case, that is, resistance is 1000 ohm. 1000 ohm times the current is 8.6 milliampere times 8.6 milliampere, and that's 8.6 volts. 8.6 volts across this first resistor. 8.6 volts. Okay, but if we drop 8.6 across this first resistor, what are we left with here then? Oh, we're only left with 9 minus 8.6. We're left with 0.4 volts here then, all of a sudden. And all of a sudden, it's not the 4.5 volt we need for our load. Let's say our hobby helicopter, drone or something, whatever we want to drive, that we need 4.5 volts. And all of a sudden we are down to 0.4 volts because this voltage divider, yeah, what didn't work out here really is that we made a voltage divider and we had a very nice 4.5 volt, really, it was reality. But then once you attach a load just to such a simple voltage divider, you change the whole constellation and the whole resistance of the second part, and you lower it, as in this example, oftentimes you lower it, and then yeah, you get a bigger current flowing through the whole constellation, and then when you get a bigger current flowing, you drop more voltage and you lose voltage because you drop it, and the first resistor you lose voltage, and you're left with something that you really you cannot use, you don't want. So, and to prove to you that what we do here theoretically also has practical relevance, or is true in reality, I just built something up here. I put a 9 volt power source to these two alligator clips and then connect these things here to my breadboard. And as you see, we are at a good 9 volts here initially. And what we start doing now is we have two 1 kilo ohm resistors, and we connect them here from plus downwards, and then we connect them from minus upwards, and there's still no connection made. Let's bridge this connection here, from here to here. We can measure what voltage we have between the two resistors. There's a little measurement pin in here, and I take the measurement of here from the 9 volt and I put it here, and you see, yeah, not perfect, but quite 4.49 something, so very close to 4.5, so very close to the half. Reality is not always as perfect as theory. But now we do the interesting thing. That is a 47 ohm resistor, so very close to 50 ohm. Okay, now I will, the size of the connector was a little bit different. I have to replace this resistor here. It's still the 47 ohm connected to here. And you see instantly the voltage drops, and the voltage drops down to our 388 millivolts, which is roughly a little bit lower still our 0.4 volts, 0.4 volts meaning 400 millivolts. Now we have 388 millivolts, but in practice, good enough. And I take that out, that load, and whoop, we are up at around 4.5 on the voltage divider. And if we load the voltage divider, whoop, oops, we're down to around 400 millivolt or even lower. And that's the thing, you don't load a voltage divider. Voltage dividers, so to say, they break down if you load them. And if that would be my, let's say this resistor would be my play car or my motor or something, and we would be happy to, hey, there is 4.5 volts on this voltage divider, let's use that 4.5 volt, and you use it and zack, you fall down to 400 millivolt. And that's the problem of the voltage divider, you can't load it. But there are some cool solutions to this, and we'll look at one in the next video where I will remedy this with a BJT transistor a little bit, and not only a little bit, but very good. So please watch my other video, and yeah, until then.